The tangent problem of differential calculus is one of the main ideas that we'll take away from this course. So let's talk about it. When we first learned about functions, we probably dealt a lot with straight line functions or linear functions. And if we wanted to talk about how that function changed, we would just pick 2 points on our graph and then calculate the vertical change, calculate the horizontal change, and then create a ratio to describe the rate of change for the function. And for a linear function, a function that is a straight line, this rate of change is constant. It doesn't matter which 2 points you pick off of your graph, this ratio, vertical change over horizontal change, is the same. We call this the slope. It's constant over the entire function. So if our life was very linear, then this would be all we need to know. Rate of change is just the slope. It's the change in y over the change in x. But the truth is, there are functions out there that aren't nice, neat, straight lines. But we still might want to talk about how the functions are changing. So we try the same process. Pick 2 points, calculate the vertical change, calculate the horizontal change. The problem, though, is that this non-linear rate of change isn't constant. So we can approximate the rate of change between any 2 points we want, but they won't apply in other cases. So we need to come up with a way to talk about the rate of change for a non-linear function, meaning a function that's curvy. It doesn't follow a straight line. Calculus can do this by starting with a point on the function a and picking points that are further along the curve and creating a line between them. So drawing some kind of secant line, and then talking about the slope of that line as a measure of our rate of change. So this slope of the secant line is an approximation for the rate of change of this function. Notice that our function is nonlinear, but we're using a linear function to represent our rate of change. If you pick points that are too far away from each other, they're not going to do a great job of approximating your rate of change. So to improve the approximation, we make multiple secant lines. Each time, we're going to pick a point that's even closer to the point A. Our goal is to approximate the rate of change for the function f at the point A. And here we have 3 secant lines drawn. The blue secant line involves a point that is the farthest away from A compared to the other points. The green secant line has a point that's a little bit closer to A. The yellow secant line is even closer to A. And if you imagine repeating this process until you get very, very close to A, that is where you come up with a tangent line. When the second point that you pick to create your secant line is infinitely close to the point A, we call it a tangent line. So the slope of the secant line is our approximate rate of change, but the slope of this tangent line is the instantaneous rate of change. At the point A, we can say the function is changing at a rate that is equal to the slope of the tangent line. Now we've got some notation here that we should talk about. For a function f, the slope of the tangent line is f prime. And we used to use m to represent slope, but m really is attached to linear functions. So we're going to switch over to this f prime notation. But if you'd like, you can use m with a subscript tan, signifying slope of the tangent line. So here we're saying that as x, this secondary point, gets closer and closer to A, then our secant slope gets closer and closer to our tangent slope. And our tangent slope is known as the derivative of f. This is the slope of the tangent line. This is the instantaneous rate of change for our function. We can use the slope of a secant line to approximate the rate of change for any function. Let's give it a shot. Here we're looking at the function f of x equals x squared, and we want to approximate the rate of change at x equals 1 by finding slopes of secant lines from that anchor point at 1, 1 to two other points. One of the points is at 2, 4. We can see that in blue on the graph. The other point is at 3/2, 9/4. We can see that in green on the graph. And our anchor point, 1, 1, that's in white. We're going to calculate the slope from the white point to the blue point. That is an approximate rate of change. So using the slope formula, change in y divided by change in x, we can calculate the slope of the secant line. We find that it's equal to 3. So a line that connects the white point and the blue point has a slope of 3. We could use this as an approximation for the rate of change of this function at 1, 1. Let's try the other point. Now we're going to look at the green point and the white point. We want to calculate a slope of the secant line that would pass through those 2 points. So we do our change in y divided by our change in x. Simplifying that complex fraction, we see that it has a slope of 5/2. So the green line passing through the white and the green point has a slope of 5/2. We could also use this as an approximation for the rate of change. Now, we're talking about approximating the rate of change at the point 1, 1. These are two different approximations, and one of them is better than the other one. Whichever approximation involves the closest point to the location where you're trying to approximate the rate of change, that one is the more accurate approximation. So in this case, the green point is closer to our anchor point, the white point. So the 5/2 is a better approximation for the rate of change than the 3, because the 3 used a point that was further away from the anchor point. Let's work on another example where we need to calculate the slope of a secant line. We're told that a rock is dropped from 64 feet above the ground, and that the height of this rock is given by the function s of t, where t is the amount of time in seconds that has passed since the rock was dropped. We want to find the average velocity. Now, velocity is the change in distance over some change in time. Our distance is the height of the rock above the ground. So we're looking at the rate of change for the height of the rock. That's exactly what average velocity is calculating here. We're given a couple of time intervals, and we're asked to calculate the average velocity over each interval. So let's make sure that we understand all of the given information. We know that we're talking about time and how the rock's height is changing with respect to time. And we know that we're looking at 2 time intervals. So I placed each of those time values on our number line. We know that we're talking about the height of the rock changing. And so the function that we are observing is the s of t function. That represents our height as a function of time. Now I have it zoomed in quite a bit because these time intervals are so close together that we have to zoom in a great deal. This function s is a parabola. It's a quadratic function, so it's not a straight line despite what it looks like in this graph. We're just zoomed in so close that the curvature looks straight, kind of like the argument that the flat earthers are using. We're not on a flat earth, even though it looks flat. We're just so close to the curve that it looks straight, just like in this picture. What we need to do is calculate the secant slope between the points that were given. So we need to calculate the output for each of these time inputs. With these outputs, we'll be able to calculate the average velocity for each time interval. So to do the average velocity for the interval 0.49 to 0.5, I'll calculate my function output at each of the interval edge points. So I need my function output at 0.49 seconds. I need my function output at 0.5 seconds. Find the change in those two function outputs and then divide it by the length of the interval. So finding the difference from my interval endpoints for the denominator. I'm able to see that the approximate rate of change, this average velocity over this time interval, is negative 15.84. What that means is, over this time interval, our average rate of change says that we're falling 15.84 feet per second. Let's take a look at the second interval, so 0.5 up to 0.51. I already know my function output at 0.5, so I just need to find my function output at 0.51. Then I'll calculate the difference in my outputs divided by the length of my interval. Notice here that I'm not necessarily preserving the order of the formula. All that matters is that we're pairing up the points consistently. So here I'm looking at my function output at 0.51 seconds minus my function output at 0.5, and in the denominator I do 0.51 minus 0.5, so we're keeping them in sync. And simplifying that secant slope, we're able to see that the rate of change is negative 16.16. This means the average velocity over the time interval 0.5 to 0.51 seconds, our rock is falling at 16.16 feet per second. Notice that that's a little bit faster than it was in the previous time interval. So as the rock is falling, it's speeding up. It's falling more quickly. It's accelerating. So this was an example of how to calculate average velocity. It's the change in your output divided by the length of the interval that you're calculating the velocity over.